Hi everyone, my name's Sovio Roberts, and this is another DSI prep study hall for Galvanize. Um, so I put a challenge in last time in our last study hall, and no expectations that y'all did it, but I'm gonna go through a solution to the challenge that I gave. So let me find that challenge, and I'll just throw it into my text editor really quick. And then after that, I'll go over a couple problems in Learn that people have asked about. Okay, so the challenge was read in a grayscale image, or in my case, I actually read in a color image and converted it to grayscale, or at least I think that's what I did. Is that what I did? Oh, I totally did that, yes. All right. Create a dictionary where the keys are bins of 10. I made arbitrary bin sizes, actually. Count the number of pixels that have luminance. And luminance is just the value between 0 or 1, or the value between 0 or 255, or whatever range is established for the luminance. And if you're watching and you're on Slack, let me know if my audio is not working, because that's been a problem a couple times now. I'm just using my computer audio, and I'm gonna try to figure out what's wrong with my microphone. I have like this really nice mic, and I have to fix it, I think. Anyway, so the idea is that you create a dictionary that is essentially a histogram, right, of the images, and this is of an image. And this is a common thing you do with images, right? You take an image and you set bins, and you count the luminance values within those bins. Often you'll do three histograms per image, right? Where you have a red channel, a green channel, and a blue channel. In this case, I'm actually just making the image a grayscale image, and then getting you only the luminance value, right? And if you think about it, in terms of light and the representation of light that we make using pixels, for instance, we've got red pixels, green pixels, blue pixels, and together 255, 255, 255, or the full value for each of those pixels creates a sort of technically pure white luminance, right? So 255 is our maximum luminance. 0 is our minimum luminance. And so really when you have a grayscale image, you're just measuring the reflection of light in some way. Really measuring the representation of the reflection of light as it would be presentable through a computer, something like that. So let's see. I used kind of a dynamic key naming method, which we'll see. I'll code through that. And I did that using f-strings. For the technical interview, you're expected to use f-strings. Obviously, we're not going to give you a problem as hard as what I'm going to code out, but the components of what I'm going to code out should be at least accessible. And I'll share my code after so that you can look through that. How do you convert that image to grayscale? This is the kind of thing that, using Google, right? And that's pretty, there are multiple ways that you could do that, or let's say 3 distinct ways I can think of offhand that you would do that. Okay, so I'm going to go ahead and code this out. I'm going to use a couple of things. I'm going to import a couple things. Let's say I'm going to import, maybe I'll make this a little bit bigger and zoom in a little bit. So I'm going to import matplotlib.image as np image, and I'm going to import pyplot as plt, and I'm going to import numpy. So again, you wouldn't be expected to do this in the technical interview, but for the sake of solving a problem in Python, I think this is really helpful. right? If you wanted to look, if you were reading through this prompt, well, you have to figure out how to read in an image, and you know, you can just Google Python read in image, and let's look at this first thing, and notice we have here it's using CV2 and IM read, image read from CV2. If you've done MATLAB or R, IM read is a common function. IM show is another common function, right? These are just images. So there's a couple different ways you can do this. I'm using MP image. Normally, for reading in images, I would actually use SK image, and or I would use CV, OpenCV2. But I really like SK image because it has some nice filters out of the box that I use all the time. But yeah, you could look in the documentation here for IM read. I believe it's the same function. If you wanted to do it that way, right? Any of these approaches would work. So here's IM read, and you know, IM read the file name. You know, you can read it in as Grayscale if you want, right? As gray equals gets true, and yeah, there's a number of other arguments you can pass into that. So what this returns is an ND array. So this is essentially a NumPy array, and you can treat it as such. And that's part of why I'm reading in NumPy, especially with this MP image. The IM read from MP image is going to get me a NumPy array. So these are all things that you could quickly Google. You know, Google is your friend. We don't allow it for the technical interview, but you won't be doing this level of stuff in the technical interview. So now that we've got our libraries, I'm going to read in an image, and this is one of my paintings that I have a picture of, and it is, let's see, let me just see what's in here. Let me make sure it's in here. So yeah, it's this image. So mp image.imread, and I'm just gonna read this in, right? I'm just giving it the file name. imread is gonna have local access, so we're gonna be able to read it in directly from that directory. Okay, so I've got that, and PyPlot has a function called imshow, right? Image show, as do most of the image libraries that you might use. And I'm going to take this image and I'm going to display it. So I'm using the gray CMap, and basically what this does for me is it gives me a kind of standard color map. There's a number of different color maps which we can peek at really quick. I go to matplotlib and color maps examples, let's say. Again, the miracle of Google. I'm just going to be able to see, well, really just wanted to see examples here, but this is giving me a whole lot more information than I need. Luckily, there's, you know, there's another thing that's the exact same thing. Maybe this? Okay. Okay. At any rate, there are these color maps, and CMap gray is going to give me kind of a visually standard color map, and that's what I'm going to use here. And then I'm going to go plt.show. This is just to show the image, and I want to block the code at this point until I close the window. So I'm setting block to true. And let's go ahead and run this. So tellme.py, and I think we should get a display of the image. Yeah. And this is the same image that's my background. Yeah. So if we're looking at this and we're building a histogram of colors, this is a limited color palette. And so, you know, I think there's maybe 15 colors in here or so. This is all done with inks, and it's not really blended. So, you know, we have some slight variation and we would expect a histogram to show different, to show certain bins as being much more prevalent than other bins. And we're actually going to see that when I code this out. So there's a question, is that link live? I hope so. I'm going to, yeah, before I start explaining this, let me just try to make sure that this link is streaming correctly. Oh, YouTube, why do you change the links? This is a really frustrating thing. Recently, YouTube changed their format. Changed their streaming format, and they give you a new link for every stream, which is pretty frustrating. And so it looks like the link that I posted in our Slack channel was not the correct one. Sorry about that. So I'm going to back up slightly. Oh, YouTube, why? Okay. Okay, so I gave a challenge last time to read in a grayscale image. So I had a challenge last time to read in a grayscale image and create a dictionary where the keys are bins in a histogram, and there's going to be a histogram of the luminance of a grayscale image, essentially. The keys are going to be defined with F strings, and then there's going to be a count of the number of pixels that have luminance within those ranges. And we're gonna peek at this a bit. I'll just go through a little bit of this again. I just typed out all this code, but sorry, the link wasn't live apparently, and the link changed from the time that I started streaming until the time I just posted the link, which I'm going to try to find a static URL. I've been looking all over since YouTube changed their interface, and I can't find a static URL yet. So if that's something you know about, please tell me. I spent about an hour trying to troubleshoot that today and didn't get anywhere. So I'll just have to be a little more diligent, and I'll post the link as soon as I start streaming next time. So I'm using matplotlib and numpy here. I'm using matplotlib to matplotlib.image, and I'm using that to read in the image here. So mpimage.imread, and this is one of my paintings I have a picture of, and I'm going to read that in, and I'm going to display it using pyplot, matplotlib's pyplot. The reason I'm importing numpy is that, well, why don't we just take a look at this? I'm going to print the type of the image, and let's see what that is. Notice it's a numpy ND array, and in general, when you're doing any kind of image manipulation, you're probably interacting with a numpy array. We're going to try to use this numpy array in very much the same way as we would use a list, which kind of gets around maybe some of the discrepancy in knowledge you have if you haven't looked at NumPy yet, but also kind of removes some of the amazing features that we might otherwise use from NumPy, because we can do really amazing matrix operations with NumPy. As soon as you get good with NumPy, you're probably going to stop using lists very often, at least for data. Okay, so I'm reading in this image, and well, what was the other thing? So I'm using this. I'm reading it in using mpimage, but as I said before, before I provided the new link, this imread function exists in other libraries and in other languages, right? So if you're using R, then imread is going to be the same function, associated with some other R package. If you're using MATLAB, imread, it's the same function name. Same with imshow, right, for showing images. And if you're using skimage, which I pulled up just a second ago, but I'll just pull it up. I won't get into it very far, but I'll just show skimage. This is a really nice, very user-friendly image processing library. It has an imread function, OpenCV Python. OpenCV also has an imread function. It's all going to be essentially the same thing. Okay. And some of these will give you ND arrays, but all of them will give you array-like objects that you can manipulate in very much the same way that you can manipulate a NumPy array. All right, so I'm reading in the image here, and I'm going to just show it really quick, and then I'll kind of repeat what I said before. I also have to do plt.show, otherwise it won't show. And I'm blocking the completion of this script because I want the scripts to end only after I close the showing of the image. So I just ran that, and here's the image. And kind of what I said before, I'll repeat it a little bit. This has a limited color palette, and so we should expect some bins to be kind of empty and other bins to be pretty full. This is done with inks, so that's why it's a limited color palette, and there isn't much blending that happens. There is some blending in these lower luminance values, and we'd expect there to be kind of a lot of high luminance values, as we can see up around here. Okay, so we're going to build that histogram kind of bit by bit, and I'll comment this out. Let's see. Steps to building the histogram. The first thing I'm going to do is convert this to grayscale. So I'm going to make a function called RGB to gray. This is a function that you could import. I often code this myself because there is sort of a bias with this that we code into the function, and sometimes I try to go for an even mix of red, green, and blue. This is going to use the classic distribution as I understand it. So the first thing I'm going to do is separate the R, G, and B channels, and I'm going to do this in a sort of NumPy array way, just because I don't want to spend too much time breaking this out into a Python list way. But really all I'm doing is I'm taking the three channels, red, green, and blue, and I'm putting them into their own arrays, like so. And then I'm going to say RGB, and so that's our three channels for red, green, and blue. And the grayscale, and this is a miracle of NumPy. We can just mix all of these channels into one channel very easily by I'm going to say, well, red is going to get 0.2989 of the distribution. Green is going to get 0.587 of the distribution, and blue is going to get 0.1140. And I believe these are the same. This is the same mixture that if you were to use an RGB to gray function from skimage, it would be essentially the same thing. Okay, and then I can just return that gray image. Notice I don't actually need to distinguish this. I could just do return here, and that would be fine. This is going to return a grayscale image. Okay. All right, so I'm going to just test this, and I'll do, I should probably convert this to gray first. Yeah, why don't I do that? So I'll say image gray is going to get RGB to gray of the image, right? So I'm making a copy of the image, and it's going to be grayscale. And then I can just take these same two function calls, the IamShow and plt.show, and instead of showing the original image, I'm showing the grayscale version of the image now. So let's take a look at that. Oh, image is not defined. Oh, why is that? Oh, that's because I'm not reading it in anymore. Okay, there we go. Let's look at that. And then let's talk about this for a second. So here's a grayscale version of the image. And what we would imagine here is that because we have sort of flattened the color channels, the red, green, and blue channels, now we're going to have these different ranges of luminance, right? This is just luminance. This is how much light is being projected through, right? So these very, very light colors, which are, so we're going from black to white. These are close to 255, or they should be. And these very dark colors are close to 0. Some of them are going to be 0. Some of these are going to be 255. So let's take kind of a look at the actual luminance values of this. I wonder if I can just print this and get some information out of it. This is going to look terrible in my terminal. But yeah, no, this is perfect, actually. So something I'm going to point out to you is that these are not 0 to 255 values, right? These are 0 to 1 values. And one of the things that I mentioned before, so these are each of the pixel values in a massive array, right? What I mentioned before was, well, how do we turn this, if it's between 0 and 1, how do we change that to be between 0 and 255? Turns out that's really easy to do, and I'll just do it. So we're building, again, we're building a histogram for the grayscale version of this image. I'm going to write a function called build image histogram, and I'm going to pass in an image, and I'm assuming grayscale on that image. Actually, I'm not. I'm going to assume that it's a 3-channel image. Yeah, I'm going to assume that it's a 3-channel image. So yeah, I'll just assume that. I don't want to get too much in the weeds. I was thinking maybe I could write this to be flexible so you could pass in a grayscale or RGB image. We'll just assume an RGB image, because even when you're viewing most quote-unquote grayscale images, you're actually viewing a 3-channel image. That's very common. So this little snippet up here, I'm just going to reuse this, and I'll comment it out. And I'll do this. Image gray gets RGB to gray of the image, and I'm going to build a dictionary for the histogram. And I'm going to create the initial bin for this histogram. It's going to go from pixel values 0 to it's going to go from pixel value 0 to the to 0 plus the bin size. Okay. So in my original prompt, I said something like, "Oh, make the bins 10 pixels wide," but I'm going to make these bins arbitrarily wide. Cool. And let me think about converting the image to 255. So I could have done that. I could have done that up here, but I don't think I will. I think I'll leave this simply as it is. Yeah, I'll leave this as it is, and I'll do it somewhere in this function. Yeah, I'll just do it. It's the kind of thing that, usually you'd build a conversion function to do, but I won't do that because it is so kind of boneheaded. It's kind of easy. So I'm going to populate this dictionary's bins. I'm going to say from bin low, for bin low, for the low end of the bin, which is always going to start at 0, and is going to go up to, well, I'll just say 255. I don't need to do 255 plus 1 here, because I'm going to handle the final bin, which let's say we're traveling by tens, right? The final bin is going to be 5 wide, right? And in that case, if it's 5 wide, it's different from all the other bins, so we have to handle that specially. So I'm going to travel in my range by bin size amounts, right? So if I have bins bin size to 20, then my first bin is going to be from 0 to 20, right? And then my second bin should be from 21 to 40, etc. So let's see if I'm thinking about this correctly. All right, so from bin low, if bin low plus the bin size, and this is going to be the majority of these, is less than 255. Does that make sense? So if I'm at 250 and my bin size is 25, then I need to do something else because that's going to be a special smaller bin. And I'm going to go from the next bin value, so f string of bin low plus 1 up to bin the low end of the bin plus the bin size, okay? And otherwise, I'm going to do something a little bit different. I'm just going to copy this whole f string, and instead of going to bin low plus the bin size, I just want to end at 255, right? So we'll just have a truncated bin all the way at the end. Okay, I think that works. I have a bit of a redundancy here. That I haven't accommodated. I think I want to go from, I don't want to go from 0. I think I want to go 0 plus the bin size. And then 0 plus the bin size. Yeah, that's what I want to do. So I'm going from 0 to 0 plus the bin size. And then I start counting at 0 plus the bin size. And so this first value, bin low plus 1, is 1 past 0 plus the bin size. So that looks logically sound to me. I might be missing something. We'll double check it when we actually get this running. Okay, so for I'm going to traverse this big matrix, and I'm going to do this as if it's lists of lists. So we can kind of think of lists, right, as being something like this, right, here, and then here, and then here, right, and then this is just going to be, you know, values. And you can imagine this being an image of some sort. If this is an image of some sort, you know, we can represent this as a list, and we can traverse it like a list. So I'm going to do that. I'm going to traverse it as if it's a list. This is not the only way to do this, but it's probably, I think it's a little more accessible for what I'm doing here. We're just going to treat this like it's a list. So I'm going to say for the y value, or the essentially the row value in the range from the length of the image, right? So the length of image gray, and then I'm going to say for x in range the length of image gray sub y, right? So for each row, and so that's going to allow us this traversal. I'm just going to print really quick to show you what this looks like, and to verify that we are indeed traversing the image. So this is going to be it's going to be some text that flows, and that's going to be fine for what we want to see here. So I'm just going to do this. For x in range, right? Okay. I'm not seeing any errors, so let's just see what this does. Okay, set object is not subscriptable. Oh, of course it's not. So what did I do wrong here? Notice my dictionary definition here. This dictionary, I want to have this key associated with a count of the pixels within that bin, and I didn't put a count in there. And so basically what it's saying is like, hey, you don't access items in a list in that way, right? And that's why I'm getting errors on line 45 and 47. Okay. Okay, what now? Key error, 11 through 20. Oh, again, I didn't assign initial values to these for some reason. There we go. So I think that should do it. Yes, perfect. And so notice we're traversing the entire image, and this is going to take a little while because the image is not tiny. And so that's it. It just finished. And these are all the luminance values between 0 and 1. So let's go from there. So instead of printing these out, which obviously we don't want to do, I'm going to get a pixel value. Okay? So I'm going to say pixel value, and all I have to do to convert this to a luminance value between 0 and 255 is multiply by 255. That's all I have to do. So I can just do image 255 times image gray sub y sub x. And I could leave these as floats. I could convert them to ints, but I'm just going to leave it as a float because I'm going to do just a little trick in this next line of code to put these pixel values into their bins. And I like this trick. I don't know. It might be a little bit confusing at first. So let me talk through it. So I'm going to take the bin size and multiply it by the pixel value, which I'm going to floor divide by the bin size. Does that make sense? So what am I doing here? I'm taking the pixel value. So imagine at this point, this is 133. And we've got bin sizes of 10. And so if I floor divide by the bin size, 133 floor divided by 10 is going to be 13, right? It would be 13.3, but we're dropping the 0.3. And then, so I've got 13, and then I can just multiply that by the bin size again, right? So that's 13 times 10, which is 130. And if our bin size is, let's see, this will allow us to reference the correct key in the dictionary as d sub binlow plus 1. Okay? For all keys except for 0. And or for that, oh yeah, that might be a problem. Well, we'll discover if that's a problem, and we'll find a workaround if it is. Okay. All right, so this is how I'm getting into my bins, is with bin low. All right, so that's just a conversion of the pixel to a floored value of the pixel according to the bin sizes. Again, this is this is more difficult, much more difficult than what you are going to do in the technical interview. But I gave this challenge before, so I just wanted to try to give a good solution to this. Okay, so if our bin low plus the bin size is less than 255, right? This is the same logic that we used up here. Then we are going to increment this value, right? We're going to increment bin low plus 1 to bin low plus the bin size. We're going to increment that by 1. There's a question that is this type of question that will be, is this the type of question that will be in the technical interview? No. No. But what will be in the technical interview is manipulating dictionaries. And I am manipulating this dictionary in order for us to get a view of the histogram of an image. So you will be expected to work with dictionaries, not quite at this extreme of a level, where I'm using a little bit complex logic to determine the bins of the pixels. You will need to use f-strings in the keys of the images. You will need to use f-strings in the keys of your dictionary in the technical interview. That's a skill that we expect you to be able to use. Okay, so back over to this. So if, I'll just try to account for this bin low of 0. So if bin low is 0, then I'm going to take this initial key, right? This 0 to 0 plus the bin size, and I'm going to increment that, right? So this is going to be plus gets 1. And then in any other case, the else case here is something that's in the final bin, right? And so this is just going to look like what we did up here. This d sub bin low plus 1 all the way up to 255. Okay. And we'll just increment that one at that point. And so that may seem like a lot of logic in there, but that's about it. And so I'm going to return the dictionary, and then so what we're going to see here is counts of the pixels. Oh, here. I've got an error here. Let me just correct that. D sub that key. Let me make sure. Okay, that looks good. So I'm going to get out some dictionary. I'm just going to call this image dictionary. And I'm going to say for key value in image dictionary dot items. And this is something you'd be expected to do, right? Common practice of going through printing out the values of the key, the keys and the values in association with each other. So I'll just go ahead and do that. And I'll do that again with f-strings. So this is going to take a little bit to run. I probably have an error or two in here that I'll have to troubleshoot, but let's find out. And again, it's traversing this entire image pixel by pixel and counting the pixels that belong in each bin. And we're doing the default bin size of 10. So just letting that run. Oh, there it is. Cool. And luckily these are in order. So that's cool. It turns out that we have very few low pixel valued items, and all those dark grays and blacks are between pixel value 51 and 60. So let's take a look at that. Let's say Grayscale color picker. I guess let's try that. So let's do what was that? That was 51 to 60. And let's just take a look at this image. We're expecting that to be between these values, 51 to 60. And this is just to kind of verify our shades here. And maybe what I'll do is just display that grayscale image one more time. And I will not call out this function. Again, when you're working on a problem, playing around with the problem, however you want to think about it, you want to verify what's happening and verify it against some third party. Here I'm just assuming the validity of this color palette from W3 schools. I'd be surprised if it was wrong, but maybe I would use a different program in general in order to do that. And so looking at this, let me just peek back over here. So we're talking about between, what was that again? We were talking about between 51 and 60. Oop. And what I'm showing here is, is these three shades. And if we kind of just peek at this, I can see that, right? Like this shade up here, right, looks a lot like the darker shades in here, like here, right, or here, or here. I actually thought they'd be darker, but kind of looking at it closer, that could be the case, right? Or these shades down here as well. So either there's some logic wrong and I'm not catching some of the darker shades. I don't think that's what's happening here. I think these shades actually do fall in those ranges. And I can likely verify that later. Okay. All right. Spinning wheel of death. Let me just, I guess, kill Python for a sec. Okay, that worked. All right. All right, so let me comment these out. We're gonna take for granted at the moment that our logic is correct here. I'm not sure how it wouldn't be, so we'll just sort of go forward with that. There's a great question here. What property of the image would most impact computation time? If you're traversing the image pixel by pixel, if you're traversing an image pixel by pixel and not using matrix operations, I'd say that pixel by pixel looking in serial order, right, where I'm looking at each row of the image and going across left to right and looking at each pixel and then going to the next channel and doing that again and then going to the next channel and doing that again, that would impact computation time because it's almost like each process would be waiting for the next process, and the processor under your actual central processor would probably handle that in a mostly serialized way, whereas if you could do a larger singular matrix operation in order to get these numbers, like look at all the rows at once and do a count of the pixels on each row, make a counter type and run that against each row, then that could be split across a GPU, or it could be better multiprocessed by your central processor. So it's mostly the way that I'm doing this right here in this pixel by pixel traversal as if it's a list. This is not efficient. It's fine for what we're doing, and mostly I want to demonstrate this in this way because this will always work for you, and you're not going to generally be dealing with image data until you have your base Python in a stronger way. I hope that makes sense. But sort of this operation up here, this RGB to gray operation, where I'm taking each channel and pulling them out of the image and then multiplying them each. This is a massive matrix operation that takes almost no time at all, but I'm building a whole new image and I'm transforming every pixel of an image and making, this takes no time at all, whereas this traversal and tabulation of pixels, because of how I'm doing this, takes a long time. I hope that answers your question. Okay, so I've got this histogram, and this is cool, right? This is the counts, but I'm going to make it more of a pure histogram. I'm not going to make it a bar of counts. I'm going to make it percentages. But before I do that, maybe I'll change the bin size to 25 just to demonstrate that this works with other bins. Hopefully, maybe it doesn't. I guess we're about to find out. Because, looking at this, binning by 10, actually binning by 10 looks pretty good here. But, terminated 15. Oh, no, that's fine. That's because I terminated the Python process before with the image display. I'm sorry. I am not actually doing anything. I'm not printing anything. Let me run that again. Yeah, so I'm just testing to see if it bins by 25 as well. And we'll get an error if it doesn't. But yeah, this method of developing keys seems to have worked fine. Okay, there we go. So here's another representation of the histogram, just with larger bins, and my final bin, notice, is 251 to 255. I think binning by 10 is a little nicer here, and we're going to convert this a little bit. So I'm going to convert this to frequency instead, and I'll copy this, and I'll just do a very simple conversion. So I'll just do something like this. I'll just notate it, convert to frequency, and all I need to do to convert to frequency is take the total number of pixels, right? So that's the sum across all the values in the dictionary, and I just need to divide each of these bins. I guess it would be these bins up here. I just need to divide each of these bins by the total count of pixels, right? So that's going to get us a frequency histogram. So what I'll do here is I'll just say v divided by the length of image d dot values. No, sorry, not the length, but the sum of image d dot values. And so this should get us percentages. Sorry, not percentages, but probabilities, or something that we can think of as probabilities, right? If we were to ask the question, if you select a pixel at random from this image, what is the probability that it sits in the bin 151 to 175, or sorry, 151 to 160. So let's see if that's working. And we're just waiting for it to run. I could have used a smaller image, but that's okay. Oh no! Built-in function or method, object is not iterable. Sum of image d dot values. Oh. Dot values is a method. So I didn't actually call it, and it's saying the built-in function or method object, because that's what I was looking at without the parens. Of course, I can't sum those values. So let's try that again, and hopefully this time it will not fail, because of the time consumption mostly. And I promise I'm almost done with this with this exploration, and then we'll get into the normal answering questions and addressing questions. Okay, so here are our probabilities, right? So what is the probability of getting a pixel value between 171 and 180? Well, it looks like that's 9.1%, right? Or a 0.091 probability. So that's kind of nice. And maybe what I want to do is maybe I'll change the bin size to 25, and maybe what I'll do here is just create a visual representation of this, and then I'll hand this code off to you if you want to play around with it. Of course, you can read in any image. You just have to change the name here on line 22 in my file, line 22. Give it a different image. Give it a different image name, and it should work fine. As long as it's an RGB image, and there's a chance that it won't be. But if it's RGB, it'll be fine. Okay, so for cave, oops. Let me grab that, and let's create a terminal. I'll just call it a terminal histogram. Terminal visual, something to differentiate it from the prior thing. Okay. All right, so this is kind of convenient. We've got this percentage, right, that we're getting out of this. What we can do with this is convert it. Sorry, we don't want to actually convert it. We want to think about a certain number of asterisks. And maybe I'll just say 30 asterisks, and maybe that'll be a good size for what we're trying to do here. So that'll be 30 times that, right? And notice this is going to be a float number. I actually want it as an integer, and I'm going to take the string asterisk and just repeat it 30 times. Oh, that's probably too low. Yeah, I think that's probably too low. Let's do, let's try 100 and work back from there. I think that makes way more sense, given the percentages we're seeing with bins of 10. Let me do 80, and I think that'll be fine. Okay. So this is just simple visual trick. I could throw this into a matplotlib plot. I don't want to take up too much time doing that. I just want to show you a simple terminal visualization of the histogram. And oh no, can't multiply sequence by non-int of type float, because I did not cast this to an integer. That's exactly why we cast to an int. And then we wait one more time. And hopefully this is the last wait. We'll talk about it for a split second, and then I will get to your questions. There we go. So this isn't the prettiest histogram because the indentation's a little bit wonky, but that's okay. We can definitely kind of get a read on this, though, and maybe what I'll do is, it's a little bit hacky, but I'll just do this and move it over, and we'll get a clearer view of it if we do this. There we go. So just imagine that this extra text isn't right here. So this is the histogram of our image binned by 25, and we can see that the modal value is between the modal bin is 151 to 175. So most of our luminance is going to fall in here, right? And you can imagine, you can imagine, we've also got these two bins, which are virtually symmetric, right? And then we've got some very high luminance values up here. Once we're up here, we can't really distinguish between them. And then we've got some low luminance values here. So that's just a quick visualization, quick building of a histogram. I'll take this code and I'll throw it into the Slack. And all you have to do is change the image name, and you should be able to run this, play around with it, do whatever you want to do with it. Cool. So I'm going to delete all of that. Actually, there we go. And I'm going to go back to a question. There's a question in here on one of the challenges in Learn. And yeah, let's just see what this is. Challenge 3, removing a dictionary key. So let's come down here, remove a dictionary key, write a function called delete duplicates. This function should take in a dictionary as an argument. This function should go through the values inside the dictionary and remove any key value pairs where the value occurs more than once inside the dictionary. Okay. This function should remove the second occurrence and on from the second occurrence of the value, but it should preserve the first occurrence, and you should not modify the original dictionary. Okay, so this is called delete dupes. So delete dupes, and it takes a dictionary. It is going to, let's just call this d out, and I'll do dict.copy. So there's my copy, and then when we're all said and done, we should remove d out, or sorry, return d out. Okay, so this is one of those functions where I'm gonna just make a dictionary here. So I'm gonna make a dictionary d, and I'm gonna populate it with stuff. And I'm gonna do this in a really kind of boneheaded way. 2, 3, 4, 5, 6, 7. And let's have 1 be cat, 2 be dog, 3 be cat, 4 we'll make dog again. We'll just do bat, weasel, and let's just do another bat. So what we'd expect to see when this is when this is run, we would expect to see the removal of this and this, right? The removal of the second cat and the second dog, and the removal of the second bat down here. So that's what we would expect to see when we run this. So delete duplicates. I'm just gonna put this down here so we can run it easily. Just say delete duplicates of D, and we'll print the results of that. So right, that's our expected out. Okay, so what I can do here is say for key and value in the dictionary, in D sub out. This is one way I could do it. There's actually a way that I would prefer to do it, but let's just do it this way first. I'm just gonna do this. I'm gonna make something called, I'm gonna call it uniques. I'm gonna make it a set. And I'm gonna say, how do I wanna do this? If V is in uniques, then I wanna delete D sub out sub K. And then I'm just gonna say uniques dot add, and we're gonna add the value. So let's see if that works. Oops. Why is that? Uniques dot add. Oh, that's because this is a dictionary. It should be a set. That's a common mistake I make. In fact, that's why I use the dictionary constructor instead of using the curly bracket form of the dictionary constructor, because I confuse these still. Okay. Dictionary change size during iteration. Oh, of course it did. you know what? I'll just do this the way that I prefer to do it, which is to initialize a dictionary. And I'm going to say for key value in d.out, if the value is in uniques, I'm going to change this to not in uniques. Then I'm going to say d sub out sub key gets value. And then I'm going to add the value to the set. So I think that'll work. We get cat, dog, bat, weasel, which is that what we expect? Cat, dog, bat, weasel. Okay. So let's see if that satisfies the criteria. This might be a bit of a red herring, this dot copy. You don't need to use that, as you can see with what I did. I think I prefer to do this, but I'll show how to do it with dot copy as well. I'll just test to see if this one works correctly. Oh, it didn't. Name D is not defined. Interesting. There may be an error with this. Let me just see what's going on here. Name D is not defined. Oh. Why did it work over here? Oh, I see. Okay. Yeah. That's why it worked over here, because I named it D down here. I named it DCT up here. There we go. So that works the same way. There we go. I think this will work now. And if it doesn't, we'll fix it. There we go. Yeah, so that worked. Let me code a slightly different solution where I make a copy, right? So dout gets gets dct.copy, and I just wouldn't do it this other way, but that's okay. I'll look at the solution that we have here that uses .copy. So for key value in dct.items, if v is not in uniques, yeah, I just wouldn't do it this way. Let's see how they're doing it here, how we're doing it here. Just take a look at this. Okay, so delete duplicates. Return dictionary gets the dictionary.copy. Occurrence list, so this is happening with a list. For pairs in past dict.items. So this is a tuple. If pairs sub 1 is not in the occurrence list, the occurrence list.append pairs sub 1, else delete. Okay, yeah. I was gonna, this is how I was gonna write this, but it just doesn't seem as clean to me. I don't recommend using .copy here. It's a reductive approach that you don't need to do. If you want to make this copy, you can just traverse the dictionary and avoid putting in duplicates by simply checking in this uniques value, uniques set. Okay, yeah. There's a great question in there. What is the cause of the dictionary change size during iteration? So the reason why we couldn't just reduce this, right, where I say for key value in dout, right, let's say dout.items, if the value is in uniques, d out. So let's try to delete d out sub key. The reason why we can't do this is we're literally modifying the thing that we're iterating over. And that's changing the size of the thing that we're iterating over. And kind of on a processor level, one of the reasons why dictionaries are so fast is that we can, they're not ordered, and each key value pair is independent of every other key value pair. And so the processor can multiprocess, but using a for loop, it can multiprocess. And I mean, this is going to be true for a list as well, right? In general, you have loop independence, or you try to have loop independence in your for loops. It's kind of a comp sci topic that we don't need to get into. But if you have loop independence, then in order to have loop independence, you need to know how many times the loop is going to run before you actually execute it. And we know how many times based on this d out dot items. This is a fixed amount of times. And so let's say we go through this and we're at the 4th time, and then the 5th time we've deleted the thing that should be in there. It's going to say, oh wait, I thought that this thing was this long. It turns out there's something missing. And so we kind of lose the value, kind of the optimized value of the for loop in that event. So it's just, oh, whoops. I need to save this in order to get that error. Oh. Wait a minute. Did I just... Oh, I know why. Or I think I know why. Still have this other code in here. Let me run that again. Okay, there we go. Yeah. So we're changing the size of d out as we iterate over it. And that's going to throw an error. Yeah. So I hope that clarifies why we get that. It's basically that we need to know that before the for loop executes, we need to know how many times it's going to execute. And if it's executing, but it finds out that it can't execute as many times as it expected, then it's going to throw an error. Cool. So let's think about more dictionary problems. Let's look at, I don't know, let's just play around with something. So let's look at Euclidean distance. And, oh, how do you avoid this error? How do you avoid this change size during iteration error? Don't add or remove items to the dictionary that you're iterating over. The reason we're getting that error is that we're deleting something in here. It'll be a better practice. Like, we don't need to delete anything in here. We can straight up do this. We can just say d out is a dictionary, and we can traverse this original dictionary dct, right? For key value in dct.items, if the value is not in uniques, then we can then we can say d out sub k. We can just add the value to that, right? So this is not a reductive approach for the thing that we're iterating over, right? We're not changing the size of the thing we're iterating over when we do this, and we're just doing it with a copy. Not a copy, we're doing it with a fresh instance of a dictionary. So that allows us to not have this error. So I mean, the short or the kind of general answer is don't modify the length of the thing that you're iterating over, right? This could be a dictionary, set, list, right? String. Although I'm not even sure if it would allow you to modify this in any. I guess I could experiment with that, but I would never even try to do that. Anyway, don't modify the length of the thing that you're iterating over with a for loop, right? If it's a while loop, it's a different story, right? Because we don't know how many times a while loop will run. That's a different thing. But we need to know how many times a for loop will run. We need to have a fixed number of times before the for loop executes, and that has to stay consistent throughout the execution of the for loop. So don't modify the length of the thing that you're iterating over with a for loop. Instead, make a copy of that thing or a collector for that thing and simply reduce the copy or, add to the collector. So that would be my rule of thumb as far as that goes. Yeah, let me know if that didn't clear it up, and I can talk about it a bit more. And I'll leave this up here. Okay, so there's this thing that we do where we ask you to code a function, right? And let's consider the Euclidean distance function. And the Wikipedia article on this can be a little bit terse. So Cartesian coordinates are 2 points in Euclidean space. So Q1, P1. It's kind of nicer to see this as x, y. So maybe I'll think about this. Maybe I'll find a different representation of this formula. Q1 minus P1 squared plus Q2 minus P2 squared. So when we're thinking of P1 and Q1, we're thinking of vectors. Okay. You know what? Let's code this out, and maybe I can disambiguate it while we're coding it. Okay. So let's consider how they're defining P and Q here. P and Q are 2 points in Euclidean n space. Well, what do we mean by that? If we're thinking 3 dimensions, right, then we're thinking of an x, y, and a z axis, right? You know what? Let's just get an easier representation of this. Euclidean distance formula. I want to say 3 dimensions, and then we should get an x, y, z out of this. Yep, there it is. So this is an easier representation of this for our purposes. This way we're not trying to think about this in terms of high dimensional vectors necessarily. Although maybe we should okay, you know what? I'm just gonna write this, and if it's inspirational, we'll modify it for arbitrary length vectors. How about that? Okay. So we're considering the length between A and B, and maybe I'll just talk about what this looks like, using a palette here. So we've got X, Y, and Z, right? And we've got these points. Let's say we've got a point here and another point here. And we've got, we're trying to measure this distance. So what this looks like is let's go back to red. This is going to be x, we'll call this x1, comma y1, comma z1, right? And this is going to be x2, comma y2, comma z2, right? And this is simply how we are defining this. So we go x in, y up, and then we go z back, right? So let's think about it like that. And I'm considering this to be x, this to be y, and this to be z for our purposes. Okay, so the formula here is pretty straightforward. It's just the square root of the square of the differences of each point summed. Okay. So let's write this function, and we'll simply we'll say Euclidean distance, and we'll assume 3 dimensions. Okay. And this is going to be, how do we want to put these in? Let's do tuples. And we'll assume, so let's say, let's call this 0.1, and we'll call this 0.2. We'll do it like that. And we're going to consider points 1 and 2 to be tuples. So let me define points 1 and 0.2. And point 1 is just going to be our x, y, and z, right? And we'll say 5. We'll just do 5, 5, 5, and we'll do 1, 1, 1, just to keep things simple. And we're going to call Euclidean distance, and just copy this, on 0.1 and 0.2, and we'll print the outcome of that distance. So if we're looking at this function, if we're looking at this formulation, this is fairly simple. We can just return something square rooted, right? Let me just do that first. So easy way to get the square root, right, to the 1/2. And this is going to be 0.2 square, the x difference is, the difference of x is squared plus the difference of y's squared plus the difference of z's squared, okay? And all of that square rooted. And now I can put in, I'll just put this in exactly as we're seeing it here. So this is 0.2 sub 1, 0.2 sub 0, right? This is our x. 0.2 sub 0 minus 0.1 sub 0. Let me make sure that I'm, yep. The reason why I set this up and then filled it in is just to keep myself organized, because it's easy to miss certain things in here. And then we'll do sub 2 minus sub 2. So I think this will work. That looks to me like it should work. This should be the distance between 0.1 and 0.2. And we get cat, dog, bat, weasel. Let me just comment out this print up here. And also clear our terminal. So this gives us a distance of 6.92. Okay, that's what we're seeing there. Now, we could write a function, and I'm just sort of winging this. We could write a function that holds all values constant except for a change in 1 point's x value, right? So we could populate a dictionary and look at the differences, the distance changes across all other things held constant except for one change in the x values. That's an analysis that we could do. So why don't we do that? Let me think about how to do this, but let's call this def analyze distance change, okay? And we're going to put in a 0.1 and a 0.2, and let's let's put in something called val to change. Great. I'm making more work for myself than I need to, but let's say val to change, and let's say by default this is going to be 0.1 x value. So notice what this gets us. This gets us 0.1x, 0.2x, 0.1y, like all the possibilities. This gives us those possibilities to change. Okay. So something to keep in mind, these are tuples, and they'd be easier to play with as lists, but let's not worry about that. I'll just treat them as tuples, and I'll convert them when we need to convert them. Okay, so let's say that we've got a dictionary, right? And I'm going to, I'm going to say, oh, I need another value in here. So that's our value to change, and we want to go from, let's only deal with whole numbers, and let's go from the original value, right? So 5, and we'll only increase. So let's do a scalar value to add. Oh, let's just call it to add. And we'll set that when we call this function. So I'm going to set that to 10. I'll go ahead and build the function call down here. So print, let's do that. And let's do to add is 10. So we're expecting to get back a dictionary that shows all the distances between 555 and 111, and 655, 755, 855, all the way up to 1555 to 111. Cool. That's the plan. All right, so let's start this off kind of let's start this off easy and only consider the 0.1x, because I think I maybe put too much complexity into this for a quick solution if I don't do that. So I'll just say for I don't know, for val in range, let's say num in range, and let's say that will be 0.1 sub 0, so that starting val of 5, all the way up to add plus 1, so that'll be inclusive of 15. We're going to get the Euclidean distance between a modified version of 0.1, okay? Now, maybe what I'll do here is just make a quick copy of 0.1. So 0.1 underscore and 0.2 underscore, I'm just setting up for later. These are going to get a listified versions of 0.1 and 0.2. Okay, so now we're going to traverse instead this 0.1 list, and we're going to get distances on the modified versions of 0.1. So in this case, we're going to say 0.1. We're going to increment we're going to change the positional value to num. So why don't we do that? So 0.1 underscore sub 0 is going to get num, and then we can just get this value here. Oops. Is that it? Yeah, I think that's it. So we can say d sub, and I'll go ahead and cast 0.1 to a tuple here, and I'm going to make the whole thing a tuple. Okay. And hopefully this won't look like a nightmare when it comes out, but you know, kind of just building this as we go and experimenting with something. So I think, yep, we want that whole thing to be a tuple, and we're getting the Euclidean distance between these 2 points. And when we do this, we're modifying the x value of 0.1. Okay, so let's do that. Let's return the dictionary and find out what this is. So I'm going to say for key value in range, not in range, for key value in, and I'll just get my dictionary out of this. Analyze, oh, whoops, let's do this. Let me grab that. For key value in analyze distance change between 0.1 to 0.2, we're adding 10, so we're getting all the distance changes of 0.1 underscore x, which is the only thing that we can do now. In d.items, let's print the key and the value. And let's find out if this works. It looks like there's an error somewhere. Okay, Euclidean distance. What's my error here? It's probably not going to be helpful. Is it just a parens error? Why don't I do this? Instead of casting this to a tuple, let me make this an f string. It'll be a little nicer to look at. I don't know why I didn't do that in the first place, actually. Okay. And then open, oh, I just have an extra paren, don't I? Yep, okay. So 0.1, and we want to go to 0.2. So this is going to be the distance between, oh, you know what, let me actually cast this to tuple. It'll look a little nicer than if it's than if it's represented as a list. And maybe yeah, I think that's fine. I think that's fine. Let's find out if that works as expected. It does not. Okay, so where am I running into an issue? Line 37. List indices must be integers or slices. Is that a list? It is a list. Okay. I just named it a list instead of a dictionary. It should be a dictionary. Oh, and everything is 0. That's excellent. That's what I was going for. Let's find out why. Let me make sure this first one. So that first one is getting us a proper distance. What is happening in here? Gets Euclidean distance 3D for 0.1 and 0.1. That's, you know, a distance from a point to itself is 0. Awesome. So this works as we'd expect it. And I'll comment that out just for good measure. Okay, so let's just take a look at this. And Then I'll switch gears and answer the question that is in the Slack. Okay, so we can watch this distance change, right? And this is kind of a linear change, isn't it? Now, what if we were changing more than one value, right? What if we were changing two values? That might be interesting. I only built an accommodation for changing the x value here. And, oh, why is it only going up to 10? I actually meant to do, I meant to do point 0.1 sub 0 plus to add. I wanted to go up to 15 and see what that looks like. So kind of what you can see here is that as we stretch just the x value and hold everything else constant, that linearly that is a linear growth, right, of our line. It's simply going growing linearly, but it's by how much, right? How much is it growing linearly, right? This rate of change, if we look at this, is so this is around 0.6 something, right? It's not, so we change by 1 on the x-axis, and we change by well, more like between 0.8 and 0.9. Am I right? Yeah. Well, we should look at the rate of change, right? We should consider these distances, and maybe I'm wrong. Now that I'm thinking about it, this does look fairly linear, but I might be wrong about that. No, that looks fairly linear. If we look at it over a larger range, I think we'd have a better sense of it. My intuition says it's linear, but my intuition has been known to be wrong on things where I'm shocked that I'm shocked sometimes by some misconceptions I have about basic mathematical concepts, which is a good thing. It's a good thing that I don't hold on to them through the shock. Okay, so I'm going to pause on that. I'm going to go look at this other problem that's been asked about. So in the lesson, tuples are immutable. Challenge 3. Let's take a look at this. Okay, write a function called tuple creating tuple. Okay, this function takes 3 arguments called name tup, age tup, job tup. All right, so I'm going to just start writing this. Tuple creating tuple? Yeah. Okay. So def tuple creating tuple, and it has 3 parameters. The 3 tuples are in parallel since they contain the same number of items, and each item at a given index corresponds to the other items at the same index. Index 0 across all 3 tuples holds the name, age, and job of the first person. Okay. This function should return a single tuple where all of the values at a given index are tuples of the data for the same person. Okay. Return a single tuple where all of the values at a given index are tuples of the data for the same person? You know what? Let me write out this data first. So I'll do this function call. Oh, I see. Tuple, so name tup is not a single person, it's only names. Age tup is only ages, and job tup is only jobs. Okay, that makes sense. So let me grab these. I'm just gonna build these really fast, just so I have something to work with. And I'm I'll just put these on individual lines, I guess. And I'll say name tup, and this is going to be Joanne, Claire, and Bob. Okay, let's just do Bob. And age, do 25, 35, 45, and job, vet. I'm trying to think short names of jobs. No, can't think of any short names. Let's do, write Siegel for some reason. I don't know, engineer. Let's just do engineer. And this person's job is business. Okay. And we'll, why am I getting, oh, I know why I'm getting there. Okay. And then we're just going to call this function and print the results. And I'm assuming we're returning a single tuple, right? So the way I'm going to do this, I'm going to make a list of lists, I guess, and I'll convert it to tuples and return it. So let's do, let's just do P1, P2, P3, and I'll just, this is obviously not the only way to do this. I'm just going to do it this way, just to get us a solution. So yeah, I'll just do a for loop for I in range, and there's 3 items. I could do length of name tuple. That would be fine. I guess we can expect more than 3 people, can't we? So let's make something called people. Make it a list. And we'll say for I in range, length of the name tuple. And we'll say people dot append, and we'll append tuples. Somebody said that they hated this one with a passion. Fair enough. We're going to append, I hope I'm understanding this one right. I think I am. So name tuple sub I, right? And then age tuple sub I, and then job tuple sub I. And I think we can just return a tuple of the people. So this should convert the outer list into its own tuple, right? Which is, I think, what we want to do. And is there an error? No, I think that's it. Okay, I think that's working the way that it's designed to work. It's working through the way that I'm understanding it, at least. So why don't I just see if this runs correctly? Okay, yeah, that totally worked. And we don't have a explanation, any explanation code here, but this is how I would do this. You know what I'd probably do, and this is just for fun. I'm not expecting anybody to do this. I would say I would probably put this into a comprehension, and I would say for I in range, the length of the name tuple And let's see if this still works. Oh no, parentheses, does not match opening parentheses. Well, that's no good. Do I just have an extra? No. Let me just track through this. So open, open, close. For I in range, the length of the name of da-da-da, and I think I'm probably just missing something there. No. Oh, this is my least favorite sort of error, because it's so hard for me to see it. People.append, and I'm going to append. So that opens and that closes. Oh, I see. I'm missing a parenthesis there. No. Oh, well, that's because I don't need that. I don't need the append at all, actually. I don't need the people or the append. Okay, so this is a comprehension, and then I'm casting the results of that comprehension to a tuple, and it works in the same way. So that should pass the same tests and should be impossible for most people to read. Okay, you don't have to write comprehensions. They're nice and everything. I really like them. Don't feel it's necessary. You know, there are a lot of things that can be solved in one line, but that doesn't mean you should solve it in one line. Yeah, a tuple can contain a tuple. But you got an error that said tuple can't be in a tuple. I'm not sure what error you were getting. If you want to copy and paste it into the Slack, I could try to explain it. I think often what people run into is they try to modify the tuple. So if you were trying to modify a tuple, it's going to tell you that you can't. So maybe it's possible that your error was something like that. I'm not sure. Anyway, yeah. So you can solve this in one line, but don't. You know, don't unless you really want to. I'd say save comprehensions until you're into the DSI, unless you feel really comfortable with them. I like them. I think sometimes they're easier to write, unless you're troubleshooting your parentheses like I was just doing. Okay, so feel free to ask questions. We've got about 15 more minutes. I'm going to try to maybe generalize this function a little bit more. I'm not actually sure that I want to do that. Yeah. Maybe I do. Maybe I do want to do that. So why don't I say, let's call this point to mod, and this is going to get this value to change, and okay, let's do this. What's a good way to do this? Okay, let's make these copies first. All right, I know how I want to do this. So we're going to try to generalize this so the value to change actually changes which dimension we're modifying. So the value to change, let's say the point to change. This is either going to be 0.1 or 0.2, right? So why don't I do this? I'll just do this in a simple way. If value to change sub 0 to, right, we can look at the indices. So 0, 1, 2, And so it's not inclusive. So if that is equal to 0.1, right? Then, or I could just single out this, right? So I could just say if value to change sub 2, and I could just change that to 1, then we're going to do something, right? We're going to change this. And let's say, let's change 0.1 to the changing point, and 0.2 to the static point. No, that does not make sense. Let's do this. Then let's make this the list of 0.1. Okay. And static will be the list of 0.2. And otherwise, it'll be the reverse. How about we do that? Okay. And we'll just switch these around. Okay. So changing 0.1, if we change this to 0.2x, then we should be changing 0.2. We'll just have to modify some other logic too. Okay, so if value to change, how about we do value to change sub -1 is x, then the position, position is going to get 0. Yeah, I think this is okay logic. We'll just do this. And elif, and then we'll do an else here. So elif value to change is y, then the position is 1, else the position is 2. Okay. Let's look at that. We can say for num in range, and we'll say changing sub position, right? And we're going to go up to changing sub position plus to add +1. Okay. And oh yeah, and then we can just say 0.1 sub 0, changing position takes num, and we can say 0.1 is going to be changing, and 0.2 is going to be static, and then we can just get the, oh my gosh, is this it? I think this is it. This is it. I think maybe this is a simple way to generalize this. Let's find out. I'm not using 0.1 and 2 anymore, so I can get rid of that. And let's see. Okay, so this should still work. This function call on line 33, let's find out. So that looks like it's working. We're changing the x value of 0.1, or the changing value, right? Now let's modify this slightly. I'm going to just test this for some other values. And I'll comment that one out, and I'll comment all of these out, and let's change 0.2 and see if that works. Okay. Oh, no, that worked. Yes. Okay. So now now we're changing the x value of 0.2. So let's try the z value of 0.2. Well, I'll do it here since I'm going to change this. Or let's try the y value of 0.1. Why don't we do that? And I think this is all going to work. Yep, this is all working. And that's just to be thorough. Let's do 0.2 y and 0.2y is changing, and then we can just do 0.1 z, and we'll do 2 z. There's no reason to believe these won't work, but just want to see. Okay, so 0.1 z is working, and let's look at 0.2 z. And that's working. Okay, so why did I do this? Why are we looking at something like this? This is just a random, not a random function, but this is just some function, right? That I grabbed out of the void, and this could be any function. And the idea that we're going for here is that you can take some function, some phenomenon, some process, and you can build a way to analyze it through a dictionary, which is what we did here. We're analyzing, we could further analyze for example, we could look at the rate of change between these values, right? We could, look at the deltas here and quantify the deltas, right? We could, build a longer f string, I guess, and we could just subtract the second value from the first value, third value from the second value, right? In this case, we're reducing distance, and does that make sense? I think it does, right? If we why don't we look at this? So we're starting at let's say 1, 1, 1. So 1, 1, 1, right? So something like let's do green. I think that'll appear better. So we're looking at that, and we're going to 5, 5, 5, and I'm just going to eyeball this. So say 5. We'll do 5 and 5, and that's going to be, that looks like it's somewhere out here, right? So let's just imagine it's right there. Just eyeballing it, and I'll connect these with a blue line, and let's do that. So that's that first item, right? That's 1, 1, 1 to 5, 5, 5. Now let's look at 1, 1, 2, which is somewhere here, and that looks like it's going to be, we're looking at 1, 1, 2. I think it's going to be somewhere here, right? It's hard to eyeball these things, given that it's a two-dimensional surface that we're using to model a three-dimensional shape. So, right? So that looks like it should be a smaller distance, right? And then, we're sort of traveling further back this way. I'm not lining this up perfectly, but we're getting closer and closer to this dot over here. We're getting closer and closer to 0.2 back here. So that makes sense. Always qualify what you think is happening. That's, just an important rule of thumb. And sometimes that looks like a visual representation, like what I just did. Sometimes it looks like, I don't know, plugging something into an online calculator. You know, I do that from time to time if I want to make sure that my function is working properly. More often than not, in production, it's about writing unit tests and honoring those unit tests. That's something that, you know, that you should generally do later in the game. For now, of course, you're building your Python out and building your analytic process. Yeah, and this is just an analytic process. Of course, we could do this with pretty much any function, right? It would be kind of nice. I do kind of want to abstract this out to an arbitrary length vector for higher than 3 dimensions, and you know, that would mean that instead of, so notice what we have in here, right? This is a summation. So why don't I, you know what? Let me just navigate this in that direction. So we're gonna have a length of 0.1 or 0.2, right? And we're looking at 0.1 sub 0 plus 0.2. Sorry, the difference between 0.2 and 0.1 squared. So we could just make a for loop, right? So we've got our summation. We can start that at 0, and I can just say summation plus gets that first value, and we can just throw this inside a for loop for I in range, and let's do the length of 0.1, and this will get us something a little more arbitrary. Although we won't be able to use our same analyze distance change, you know, quite the same, right? Because this is expecting these static XYZ values, but this function should still work from this analysis standpoint. So what we're going to do is sum that, and we're going to look at sub I, right? And this looks more like the general form for Euclidean distance. So let's look at this in Wikipedia. This is going to look much more like the generalized form of this, and I'll try to relate this more closely. Here, let's look at it through the summation. There we go. So 0.1 minus, or sorry, 0.2 minus 0.1, not that it matters, squared, summed, and that's for every point. And that's exactly what we're doing in this for loop. And then we just return the square root of the summation, right? Which is, again, exponentiation to the half. So let's make sure that still works. For I in range, I'm missing a colon. And that works in the exact same way, right? So that's cool. Now, what if we wanted to, I'm not going to do this because we're at time, but what if we wanted to modify this to be arbitrary? Maybe I'll go a little over time. Let's say, let's call this point to change, and we'll default that to 0.1, and let's call this dimension to change, and let's default that to 0. Now, it would kind of make more sense semantically to call this 1, so I'm going to do that. So I'm going to say if point to change sub 2 equals 1, right? That's the point. Then we can do the same thing here. We can change 0.1. We can change 0.2. We can apply changing in static in the same exact way. But now we need to deal with dimension to change. So if dimension to change is well, we can just say the position. We can simplify this a little bit and say position to change is going to get the dimension to change -1. And then, oh my gosh, is that it? Let's just call this pause. And wow, is that it? I'm just going to try to run this. I'm going to throw another dimension in here. I'm a little afraid I'm underthinking this, but let's find out. Let's look at Euclidean distance in 4 dimensions and see if that works. No! Oh, that's because I didn't change this. Okay. We can just grab all of this and do that. And let's do, oh, okay. Let's think about this. So 0.2 and then dim to change. Oh, right, this is val to change changed to point to change. Let me just do a little cleanup here. Val to change. If you ever watch Clark code, he has a lot of nice, really quick coding things where he instantly changes all of something. I don't know how to do that in VS Code. Get me into Vim, I can do some of that stuff. But anyway, point to change, and there's going to be 0.2 and dimension 3. So dim to change is going to be 3. Is that going to work? So let's try this, and then I'll fix all these others. Let's find out if that works. Oh my gosh, I think that worked. Right? So here's our 4-dimensional points. And yeah, these are the distances, Euclidean distances for 4 dimensions. And that's kind of cool. That really wasn't that hard to abstract. I thought it was going to take a little bit more to do that. So let's say 0.1, and I'll fix my dimensions to change. And this is nice because it's a more generalized function, right? I think it's nicer to write more generalized functions. Okay, so 0.1x, and then dim to change on that is going to be dimension 1. 0.2x, dim to change is going to be dimension 1. 0.1y, the dimension to change will be 2. 0.2y, dimension to change will be 2. And 0.1z is going to have dimension to change 3. Okay, so let me just test another one of these randomly, make sure that I'm not underthinking this. Right, that's 0.1, right? 0.1 is changing, and the second dimension is changing. So what I'm not changing is dimension 4, but you know, if you want to take this code and modify this slightly to change dimension 4, yeah, then that should work fine. So, you know, the next stage of this would be to change more than one dimension, right? And see how that affects things. And then you would want to use a nested loop, potentially. Or you'd want to increment 2 dimensions at the same time for each loop that you take. Yeah. Awesome. I'm going to paste this into the Slack. And again, this, of course, this is not a problem that is going to be on the technical interview, but it's the kind of problem, it's the kind of analytic approach that you want to take at this stage. And, you know, we're kind of exploring some stuff, but you want to be creative with this, right? You want to think about coding as a creative endeavor. And you get stuck for sure in the syntax, and you get stuck in trying to logic things out. But there are so many different ways that you can solve any given problem. And for example, this is not the only way, not by far. But this is a way that works for an arbitrary, dimensions at arbitrary distance of 2 points in arbitrary dimensions. So it's one way to solve it. You can think of another way to solve it, but you want to generally be able to take some phenomenon, some function, and analyze the outputs while changing some value. When we're dealing with discrete distributions, what we're doing is we're changing the value of k for binomial or for Poisson. With Poisson, you could also change the value of lambda, or with binomial, you could change the value of n. Right? You can write very many different forms of analysis on the same phenomenon, and that's kind of cool with this set of tools. So that's just manipulation of dictionaries for this kind of problem at this stage, and that's what the technical interview generally looks like, along with your basic discrete and basic probability kind of textbook problems. Cool. All right, so I'm going to just put that code in, and thanks so much for watching, and reach out if you have any questions. Do I know the following cohort after October? October, November, December. I think it's February 5th, but I'm going to just search for that really quick. So let's say Galvanize DSI. I think they should have it listed. October 5th through January 15th. You know what? I don't know the date for sure. I thought, I was thinking that it was in early February, but it might actually be before that. It might be in late January. So that's probably a better question for an enrollment advisor. I thought I knew, and I thought that I could find it listed right here. Just I'll ask somebody, and I'll post it in the Slack when we get off of, or when I sign off. Okay, thanks so much, everybody, and I'll see you all soon.